This is Dr. Jiansong Zhang. I'm an assistant professor at Purdue University School of Construction Management Technology. And today we're presenting this technology, autonomous robotic system for building frame.
Hi, I'm Christopher Lackney. I'm one of Dr. Zhang's research assistants, and I've been collaborating with him on this project. There's a large demand for affordable, high quality, and more energy efficient buildings today.
On the supply side, however, the construction industry is facing a workforce shortage. Survey has shown that more than 80% of the companies in the US in the construction industry are having difficulties to fill the trade positions and experience the labor forces.
We view automation technology, and especially robotics, as a promising solution to address these challenges, as new automation systems could allow existing workers to build more efficiently.
In addition to mitigating the workforce shortage, the automation technology can also allow for faster, safer, cheaper, and more precise construction, therefore creating significant social and economic benefits to the society.
So here we have some figures that kind of back up what we were talking about on the previous slide. According to the market analysis firm Tractica, the global market for construction robotics is set to grow from 22 million globally per year in 2018 to 226 million globally per year in 2025. So there's significant room for growth in this area.
The other factor that comes into play is the labor force shortages that we mentioned earlier. Because of that, the market window for construction robotics is now for the construction industry to reap its benefits.
And if we look at the chart to the right and you look at the orange line, that shows productivity per worker hour in residential construction. And you can see that from 1985 to today, there has been pretty much no significant growth, which shows that new technologies really have not been adapted successfully. And so there's significant potential for benefit and innovation to be derived from increased adoption of technology in that space. And so the technology we're presenting that we believe can help address these challenges is a robotic system for the automated sheathing of timber frame structures. And so we've developed a novel end effector design that can be attached to existing industrial robot arms in order to facilitate the sheathing of timber frame structures with the device. And we've also developed a software framework, including a computer vision algorithm that should allow this system to operate successfully on the construction site. And we've developed all of the designs for the end effector in addition to developing and testing the software components, and had plans to test the full-scale device with a KUKA industrial robot arm in a laboratory at Purdue this summer. But due to COVID-19 related restrictions, we were unable to do that, but we're still ready kind of to test the technology and start bringing it into the real world. And we view this system not as just a product in itself, but as a starting point to creating a platform for construction robotics, and creating a system that ultimately is able to be very modular and complete a wide variety of tasks. So here are some competitive advantages of our technology. Currently, there's no robotic solutions on the market for the automation of timber frame construction on site. There are existing systems that do a similar task that are much more oriented towards operating in a factory environment. And we're looking to take that technology and make it simpler, more robust, and such that it's able to operate effectively on a construction site.
Our technology spin off from National Science Foundation sponsored research, and we are also in the patenting pipeline for this technology. The integration of paneling placement and fastening into one operation in our technology will allow for simpler design, lower cost, and significantly higher speed compared to the existing systems. And I would like to quickly mention the story of the Tesla Motors, who changed the conventional welding operation on building the bodies of their Model Y to the forging method, which switched the 1,000 to 1,500 welding operations to one simple forging operation, which changed the time spent in this operation from 2 hours to 2 minutes. So following a similar rationale, our technology is going to build these much faster.
So another advantage of our technology is we're offering an integrated system that includes mechanical, computer vision, and software components that allow it to kind of operate as a complete solution. And our system is modular and built around existing industrial robots, which allows for faster and more cost-effective development and need-based customization.
And our technology is also leveraging years of research results in interoperability of building information modeling. Our technology is fully compatible with the standard formats for building information modeling data. It can be used in a wide variety of different BIM operating tools and workflows from the building design point of view.
So our project is currently in the initial stages of development and testing, and we're seeking partners to help further develop our technology and bring it to market. Thank you very much for watching our presentation, and we hope to hear from you.
Hi, my name is Christopher Carangelo, and today I'm going to be talking to you about polyethylene graphene, or PE graphene, a nanocomposite film with superior mechanical strength. There are several industries that have an ever-growing need for high strength-to-weight ratio materials. Take, for example, automotive. The lighter the car is, the further it can travel on less fuel. Traditional materials like steel and aluminum, while being cost-effective and easy to produce, are becoming too heavy for the market's current needs. So the automotive industry has become more ready to adopt composite materials, such as carbon fiber, and we've seen it used in the past on supercars. However, because of its fibrous nature, it has a very difficult and energy-intensive manufacturing process, making it too expensive to be used on mass consumer vehicles. On the other end of the spectrum, there are polymer films. While they are really easy to mass produce and super cheap, they don't boast significant mechanical properties and therefore cannot be used for structural purposes. But the automotive market is not the only market in need of such a material. The ballistic vest market needs lighter weight vests. The aerospace structure market also needs weight reduction and lower mass manufacturing costs. And the sports equipment industry no longer needs to settle for lower strength, cheaper composite materials. We hope to meet the needs of these markets with our new material, PE graphene. PE graphene, simply put, is just polyethylene reinforced with 1 weight percent thermally reduced graphene, and its mechanical properties rival that of the fibrous composites that already exist on the market. Additionally, it is at a fraction of the weight and cost to manufacture because it uses already existing film manufacturing equipment and cheaper materials. As seen here on this table, PE graphene is significantly cheaper than some of its fibrous competitors such as Kevlar, Dyneema, and carbon fiber. Additionally, it is significantly more versatile. It can be used in all the aforementioned industries, while its competitors are limited to only a few. We are currently looking to finish characterization of the material by running it through tests like fatigue, strength as a function of temperature, etc., and begin case studies, specifically in the automotive industry. For this, we are looking for two things: an industry partnership that would be able to provide us with a steady stream of ultra-high molecular weight polyethylene and/or graphene oxide. We are also looking for investors to fund these case studies and test the scaling of manufacturing. We are currently looking for about $100,000 in funds to purchase the necessary equipment to manufacture this at a larger scale and begin prototyping. Thank you for listening and have a nice day.
Hello, everyone. My name is Yanliang Zhang. I'm a faculty member and the principal investigator of Advanced Manufacturing and Energy Lab at Notre Dame. Today, I'm very happy to share with you a very exciting technology we invented in our lab. The functional nanosurfactant systems for printing nanomaterial inks. First, let me give you a summary about the market advantages and opportunities about our technology. So here we invented a graphene cotton dot-based nanosurfactant with superior properties. This nanosurfactant can reduce the interfacial tension and stabilize colloidal nanoparticle systems. It can generate high colloidal stability inks with improved interfacial bonding and mechanical strength in the printed material and devices. Meanwhile, it also has added functionality due to the semiconducting nature. This surfactant makes possible many types of functional inks for diverse applications of printed devices. It's also environmental and bio-friendly. Our surfactant can open broad applications in sensors, energy conversion, and storage devices, as well as flexible and wearable electronics. It can be used for producing functional inks of various nanomaterials for either 2D or 3D printing. It can also be used for producing superior, robust thin films and coatings. This is one table summarizing the major advantages of our nanosurfactant compared with the other conventional surfactant. So we only have enhanced functionality, increased strength, but also our material is made with low-cost solvents and also non-toxic solvents. This is our target markets in three main sectors: the wearable devices, conductive inks, and additive manufacturing. They all are showing rapid growth in terms of their revenue. And I would like to give you an overview about our technology. So as you can see, this colloidal nanosurfactant system can be used to exfoliate, stabilize, and formulate 2D nanomaterials in water-based inks for 3D printing applications. And here we demonstrated this long-term stability in the nanoparticle ink enabled by this nanosurfactant. We can get over 6 months shelf life in a wide range of inks. Meanwhile, this nanosurfactant also showed a substantial improvement in the mechanical strength in the printed films compared with the same film printed using the conventional nanosurfactant-based ink. More importantly, this nanosurfactant can be used for versatile device design for a wide range of applications. And here we are showing a proof of concept device. This is a UV sensor array printed on a small glass dome. And here we can not only sense the intensity of the UV light, but also the directions. Of course, we can also use our nanosurfactant ink to make other sensors, electronics, and also for the energy devices. And we would like to explore opportunities to collaborate with industry partners to commercialize our technology. If you have interest in our technology, I would be happy to talk with you further. Feel free to contact me by email. Thank you very much.
Hello. In this video, I'm going to talk about the material data flow extraction and simulation system that we have created to map the manufacturing networks. So the reason we have developed this tool is that there is a huge push towards moving from our traditional supply chain management system, which is more of a linear system from developing to planning to the production, and then there's some feedback if there are any disruptions. So it's basically an inventory management system rather than looking into the network in depth. But what we want to move towards is more of an dynamic systems where as we can gain an visibility into how the network is evolving with the different parts of the manufacturing systems changing. So there has to be some kind of digital core, but the question is that what function should this digital core platform perform? So what does the market need is to get into the faster visibility into any of the risks that can happen when we gain visibility into the manufacturing networks of the suppliers beyond tier 1 and tier 2. So we have to create this digital supply network that can help us build resilience by simulating different scenarios or thinking about adopting technology A versus technology B. So if you have a map of the whole network of your manufacturing system based on technology A versus technology B, it can help us see really where are the risks existing and what are the wastes being generated, where are there options to actually improve on the efficiency. As per a market report, the global market for supply chain analytics tool by 2024 are going to be about 9.2 billion. And among that, the cloud-based tools have the highest growth rate, even though their share is going to be about 3.1 billion. So the cloud-based tools, which are more collaborative, is a totally unexplored market. And what we need is that we can have this cloud-based tool for the fast evaluation of options. So this is the critical gap that our technology has been built to fill by evaluating supply networks via simulation and understanding the risk of waste generation for switching for new type of feedstocks, raw materials, or different kind of technologies. So in short, what this technology does is that it automates the mapping of the inter-industry network in terms of physical flows using mechanistic models, so first principle physics-based model, process models, and a macroeconomic input-output framework. So if you have technology A versus technology B, that can be simulated on the PIoT hub, and then we can pick from the network maps, after evaluating the network maps for two different technologies, which of these technologies have a lower emissions or waste and more resilient network structure. So I'll give a quick demo of the tool here. So I'll quickly demonstrate the use of the tool. In this tool, we have developed an interface where you can upload the engineering models. So you can type a simulation name. I'm going to put biodiesel 2, and you can put any description like network of producing biodiesel to understand the dependency on different industries. And then I can upload models. So since we were also interested in the regional economy, so we have this region, but if you want to just put a particular industry name, that should be fine too. Or you can use the region of the industry where the industry is located. So this is 2012, and then I can just upload the model. So let me just say soybean production because I'm going to use the soybean model. So I'll put soybean farming. Then I can add another model. And I'll also, for the sake of the shortness of the time, I'll just demonstrate this particular system for one particular user. And this is oilseed processing. Upload an Aspen model. So I have an Aspen soybean. And I'll also put another model. So. And then I can submit the job to the server. When the job is submitted, you will get this message, and then you need to go to the output tab, and you will see something like that says the processing. So to demonstrate how once the simulation is completed, what results we get, so you will get a green status like this. I can click on the simulation completed. What we will get is we can get a heat map that basically shows what is the different industries interacting. So you can see that the fertilizer manufacturing has a huge recycling stream, which is internal, but you can also see that soybean farming has a very high input to the soybean and other oilseed processing. So that basically tells how different industries are interacting. And we can also convert it into a network view, which we have not implemented on the cloud yet, but we can do that. And then we can have a physical use table and physical supply table. And based on that, we can know what different wastes have been produced in this network. We can also see different shared models. So we can see that if people have shared models like this one, we can download and then we can modify those models ourselves and upload for our own simulation. We can also see if any user has shared results. So for example, this user Steve276 has shared their result. We can go into that and we can look at the description to use their result. So that's the quick demonstration of how this tool can automate mapping the network of the production system. And that can help us know where we can invest to actually reduce our waste or how we are dependent on different suppliers. So moving forward, in summary, this technology can help us evaluate different technological scenarios to understand how can we lower emissions and waste, but also understand the risks that a manufacturing facility can have on other suppliers' manufacturing network itself. So gaining visibility into the tier 2 and tier 3 kind of network. We can form a digital core using this cloud platform to actually do some scenario analysis and then decide which one is the best technology for us to move forward. Compared to other technologies that are existing on the market today, like SAP, SAP, which basically helps in the inventory management and a lot of supply chain management, the advantage in our tool is that we are integrating engineering-based models. So if you have a future technology, you can actually embed it in our tool and see how the network will look like in future and not just the existing one based on empirical data. And then we can also automate, which I'm not sure if SAP does, but I know that the other tools like CIMAPRO, LC, and OpenLC did not have, but also automation of quantifying waste and emissions just based on the first principles model rather than relying on some empirical data correction. So at this stage, we are looking for early industrial testers and investors to scale up and build industry-specific functionalities. As this tool is a very, very generic one, we can adapt it to different types of chemical manufacturing or pharmaceutical manufacturing, but also automotive packaging industries based on the first principles model we can create with the industry partnership. With that, I would like to thank you all for attention, and I look forward to having more conversations about our MFTES and PIoT Hub tool. Thank you.
Hello, this is David Barr. I'm the head of School of Materials Engineering at Purdue University. I'm going to be talking today about some work that was done by my graduate student, Temitope Eminu, on depositing nanoparticles of copper onto polymer fibers that are useful for filter applications. I'm happy and like to thank the Office of Technology Commercialization for providing this opportunity to talk about our work today. So there's a specific market need about creating mask materials and filter materials, in this case, filtering airborne particles, that can be antimicrobial. Traditionally, most mask materials are based on entrapment. So a virus is either kept from reaching the air if it's leaving your mouth, or if you're wearing something like an N95 mask that fits properly, viral particles are entrapped in the filter and they don't make it into the wearer that's using the PPE. So a more robust face mask design would allow antimicrobial efficacy to the mask itself. And we pick a material like a copper nanoparticle. copper nanoparticles, silver nanoparticles have all been shown to be toxic to viruses and bacteria. And so if we can have copper nanoparticles within a mask, we should have a mask that is more safe for the user or for the wearer and protect them from more things, more viruses around. Now, the size of this market is changing dramatically. A year ago, this would have been a very different discussion. So you can see estimates that range from single 10 billion to approaching 100 billion in the next 6 years. The range that masks are going to be used is going to vary dramatically. And I don't think any of us can say today exactly how big that market is going to be. However, what we do know is that if you have something that's antimicrobial and you have a mask, you want that antimicrobial component to remain a part of the mask. And so what we did in our particular approach to the technology here has been to say, we take an existing technology like electrospinning, nothing particularly new, been done for decades, and it can make a non-woven fabric. The fabric is flexible, it can be used in a mask, or it can be used as an insert in place of a mask. And what we do is we put copper nanoparticles onto that non-woven polymer fiber. So we have fibers that are somewhere between 100 nanometers and a micron in diameter, and we coat them with copper nanoparticles. The key here is that electroless deposition, also not a particularly new technology, it's been around for over 100 years. If we use the right conditions and we create the right morphology, we can get well-adhered copper nanoparticles onto this electrospun fiber mat or fiber mask. The copper nanoparticles are stiffer, they're harder than the underlying polymer. And so if you think about a fabric, if you twist, turn, pull, stretch, bend, put around your mouth a fabric, you're going to be handling it. If those particles flake off, if they become loose, if the wearer breathes them in instead of having them stay on the mask, that's a potential problem. And so we need really well-adhered nanoparticles to this polymeric mask. And our particular technology is we've looked at a way to get a specific geometry where the nanocubes are well-adhered and conform to the shape of that polymer fiber. And it's that conformal condition that leads to an extremely high adhesion of the particle to the underlying fiber. And you can see there in the picture, we stretched individual nanofibers to strains of 10, 11, up to 17%. And we see the particles remain on, even when the polymer starts to fail, the particle stays adhered. If we compare this to some of the competitors out there, most of them take copper nanoparticle solutions and immerse materials, mask material, into that solution. There's a problem with that. It wastes copper and you have agglomeration. Our technology, the only copper we put down goes onto the mask. It saves money, makes it relatively inexpensive and easy to scale up. And what we're looking for are partners to look into efficacy and reliability studies. This was funded under National Science Foundation funding. We're looking at how particles adhere to polymers. And we've figured that out. And now we need to look at how do we take nanoparticles that we know have been proven to be effective antimicrobial components in other materials and say, will that work in this mask geometry? So we're looking for collaborators to fund efficacy studies, as well as investors that are looking at scaling up production and then partnering with existing mask manufacturers to get this out as quickly as possible. Thank you, and I look forward to answering any questions you may have.
We would like to present to you silicone padding embedded in fabric. Our technology centers around silicone padding, which is created by mixing air bubbles into a silicone monomer with appropriate additives. The silicone mixture is then poured into a two-part mold, which creates the final desired shape. The permeable fabric is laid inside of the mold, and a vacuum is pulled on the mold during curing. This process allows for the silicone padding to bind to the permeable fabric material during the curing process. On the right, you can see a sample of this technology. This is in a second skin application.
Some of the commercial applications include protective garment, gear, and equipment in sports. primarily contact sports, whether that is contact between player and player, player and object, or player and surface. This can include padded apparel, which can be elbows, garments, or thigh protection, second skin, and helmet padding. Day-to-day protection includes between cabinets and padded floor, has to help in the energy attenuation of them, sharp corners for protection, and then between hard armor plate and a body has to provide a second layer to reduce any sort of impacts. In vehicles, it can be used in roll bars and cages. Short story about a possible use. Jerome, a Purdue men's rugby player, suffered a first-degree separation of his acromioclavicular joint during the game after a collision with an opposing player. The team physician evaluated the injury and stated that the player was allowed to return the game if the joint was properly protected. At first, he recommended a second skin he had in his first aid kit. However, Jerome was hesitant because previous use of this specific second skin from an unnamed company proved to be ineffective. Nonetheless, he wore our second skin throughout the remainder of the game and was able to tackle with that shoulder and not feel intense pain.
Silicone padding embedded in fabric has three major use cases. The first use case is as a second skin. Both McDavid and DJO Global products, their products are pictured below, sell for around $15 per roll. Our materials cost far less. Additionally, these padding products have poor force attenuation, which means sometimes multiple layers of this padding are required to get the desired effect. Another avenue is via padded apparel. Our padding remains flexible while providing impact protection for collisions with athletes or hard surfaces. Some examples of padded apparel may be knee compression or elbow compression. Early testing demonstrates performance on par with current state-of-the-art football padding as well.
The advantages of silicone padding embedded in fabric set it apart from other existing paddings. Our padding has superior energy absorption properties that mean in one layer it can reduce peak impact force by up to 50% above 3 or 4 layers of competitors in laboratory testing. The ability to tune properties for better impact absorption mean that the padding may be tuned for the optimal impact range of the activity, meaning a different padding may be used in rugby, football, basketball, or other sports. The permeation of our padding to various fabrics means that it may be affixed to a wide variety of pre-existing textile or permeable materials. On the right is the graph demonstrating this peak force reduction. What we are looking for is an appropriate partner to license this padding technology or to engage in a joint development agreement with the HURT Lab at Purdue University. Thank you for helping us develop this exciting new technology.
Hello everyone, as mentioned before, my name is Elvin Gary and I'll be presenting the SILSEP. To start off with the market needs. So commonly in college dorms, a lot of people elect for these lofted beds because it helps save them space because they could put whatever they want underneath the bed, whether it be a futon, a TV, dresser, desk. The world is theirs with whatever they want to put underneath. But with the lofted beds come a challenge on trying to get up into the lofted beds. As you can see, the desk on one of the pictures covers the ladder, and on the other end, there's a lot of bins that are covering it as well. So it could become rather dangerous to get up onto these lofted beds, and a lot of people have been injured with that. Continuing with the market, majority of the suppliers for the college lofted beds use a similar bed architecture. Some of the companies that make these beds is Bedloft, which is Purdue supplier, University Loft, New England Woodcraft, Iowa Prison Industry, Southwest Contract, and many more. Specifically with Bedloft, since that's what Purdue uses, they supply a lot of beds for 70+ universities throughout the East Coast and Midwest, as seen on the right. And specifically, they supply a lot to the Big Ten Conference, which is the one that Purdue's in, meaning that they have a big marketplace with the bigger universities around. Now going to the technology, the SILSEP is an auxiliary step that connects to the lofted bed railing system and creates an easy way to get up on the bed. Simply, you just hook it on to the existing railing system of the lofted bed in whatever increment you please, and you just step up and step down as you please. When you're not using it, you can put up into this rest position to allow for more space underneath. The SILSEP is made out of aluminum for its main body, which is the part that connects to the railing. along with the step being made out of high-density polyethylene, and that's all to help reduce costs for the product. One of the major design criteria we held was that the stove step needs to hold 300-pound load, and the reason why 300 pounds is because that's a little above the 95th percentile weight of a male in order for our product to cover the majority of people that are coming to the university, and that the 300 pounds is collected from the CDC. When comparing to the current technology, the current technology is comprised of the built-in ladder and the bunk bed ladder. When comparing its safety, the built-in ladder is the least safe because even though it is the largest ladder out of the three, the steps itself are polished wood, and stepping on it could potentially cause a slip, especially if you're wearing socks. And then on top of that, these ladders are rather high, and some of these dorm ceilings are rather short, so a lot of people have hit their head on top while trying to get over it. When looking at the bunk bed ladder, it is easier, safer to use because it is a more open space, but oftentimes the steps are not customizable and there's no grip tape on it, which makes it harder for shorter or taller people to stride up without any discomfort and also still potential slip. The StoveStep tries to fix both of that by allowing that auxiliary way to get up into bed, but also having grip tape and glow-in-the-dark tape on it to not only be able to see it at night, but also to not slip as easily from it. When it comes to space, the built-in ladder doesn't take up any additional space, but is often compromised due to furniture location and not being able to use due to that. Bunk bed ladder takes up the most space compared to the three because it's always in that position and doesn't move anywhere. While the StoveStep, even though it takes up a little additional space, it could be put up into its rest position to allow for less space to be taken up. When it comes to the cost, the built-in ladder is the cheapest because it comes with a bed, but obviously is not as useful as mentioned before. The bunk bed ladder, some of these can cost between $60 and $80 and include additional installation, so that's an extreme cost. While the StoveStep is predicted to be around $10 to $15 and is very easy to install, it just connects to the railing system. Finally, when it comes to accessibility, as mentioned before, the built-in ladder is not very accessible most times due to the way people configure their furniture, so often leading them to jump on their desk or the windowsill to get up into bed, which is rather dangerous. The bunk bed ladder is only accessible from the one side and also is harder to adjust to the steps for taller, shorter people, while the StoveStep could be put on either side of the bed and could be put in any configuration that is desired by the user. So shorter people could put them closer together, while taller people could put it farther apart to help with their stride. The next steps for our product, we're looking to license out the technology to a customer, maybe one of the loft bed companies, hopefully a manufacturer that's interested in selling the product. And we would also appreciate any connections to companies or personnel that would be interested in helping us commercialize our product. I'm very passionate about this product because I've been working on it since sophomore year, so roughly 2 years. And I really think it could help out students make their lives a lot easier. Thank you for listening and enjoy the rest of the conference.